Every new piece of information has a place to fit, making it easier to recall and apply. The habit of reading broadly is a key of success. The wisest way is to apply everything that you are learning, then the real results happens. I'm so thrilled that you are listening to this video today, and let's get started with the most important questions from the abstract algebra. See, this is group theory which is related to MFCS, DMS and DMGT. See here, it is given that A and B are any two elements in a group G dot which commute. Then we have to show that A inverse and B inverse and A inverse and B commute. And next second question here is we have to show that for every A comma B belongs to G, if AB whole square is equal to A square into B square, if and only if G is abelian. And the next third question here is in a group G, if A belongs to G, then order of A is equal to order of A inverse. Next, the fourth question here is the order of any integral power of an element A in a group G cannot exceed the order of A. That is, order of A power M less than or equal to order of A. See here, the first question here is so important that if A and B are any two elements in a group G dot which commute, so which is satisfying the commutative law. And next we have to show that A inverse and B commute, A and B inverse commute, and A inverse and B inverse commute. See here, it is given that G is a group and A and B are two elements in a group G dot which commute. So which commute means it is satisfying the commutative law. And next one we have to prove that A inverse B. So first one is proof 1. So we have to show that A inverse and B commute. So we have to show that this satisfies the commutative law. For that what is needed here? So it is already given that AB is equal to BA for every A comma B belongs to group G. So in a group G, A and B commute each other. That is AB is equal to BA. Now I need to show that A inverse B commute. So I am multiplying both sides from the left hand side with A inverse. So this is A inverse into BA. Now, according to, see here, associative law, as G is a group, A inverse into AB is equal to, so this can be written as A inverse into BA. So, A inverse into A, according to the inverse law, this is E into B is equal to, this is A inverse into BA. So, this value is equal to, B is equal to, this is A inverse into, this value is BA. So, we need to show that A inverse and B. So A inverse and B should communicate on both sides. So now this time I am multiplying with A inverse. See here, this time I am multiplying with the A inverse from the right hand side. So this is B into A inverse is equal to A inverse into B is equal to. So I am writing these two, that is A into A inverse. So this is B into A inverse is equal to A inverse into B is equal to E according to the inverse law. So this is B A inverse is equal to A inverse B. See here, if you observe this one, B into A inverse is equal to A inverse B. So we say that A inverse and B commute each other. So this is A inverse and B. Therefore, A inverse and B commute. That is A inverse and B commute. So here what is taken here? A and B commute each other. That is AB is equal to. See here I have taken AB is equal to BA. So this is AB is equal to BA. Now I have multiplied from the left hand side with A inverse. So and next thing here is now again I have multiplied with A inverse from the right side. So these are the two things which I have applied in order to get A inverse and B commute. And next question here is A and B inverse commute. See, in order to show that A and B inverse commute, so this is proof 2. So already we have A inverse and B commute. So we have A inverse and B commute. So which is nothing but, see here, B into A inverse is equal to A inverse into B. Just now, so it is given that B into A inverse is equal to A inverse into B. And now we have to show that A, B inverse commute. So from this, we have to apply A. So this is B inverse whole inverse is equal to A inverse B whole inverse. I am applying inverse on both sides. And see here, we have a formula that since AB whole inverse is nothing but B inverse into A inverse. First we have to take B inverse and then we have to take A inverse. For this will be A inverse whole inverse into B inverse, which is equal to here also. This is B inverse into A inverse whole inverse. So this can be written as A inverse whole inverse is nothing but A into B inverse, which is equal to B inverse into A. So if you observe this one, this is A into B inverse is equal to, this is B inverse into A. So which means that A inverse and B commute. So this is the second question here, that is A inverse. See here, that is here B inverse and A commute. And see here, now we have B inverse and A commute, and therefore A and B inverse commute. And the next one, proof 3 here is we have to show that see here A inverse and B inverse commute we have to show. So as we have AB is equal to BA, so we have AB is equal to BA, and now if I take A inverse, AB whole inverse is equal to BA whole inverse on both sides, and according to our formula this will be B inverse into A inverse and this is A inverse into B inverse. And now this is nothing but, see here, this can be written as, so this is B inverse into A inverse is equal to A inverse into B inverse. So which is nothing but A inverse and B inverse commute. Therefore A inverse and B inverse commute. See here, it is so simple if you follow these steps. First, it is given that G is a group and AB commute. So we have to take this AB is equal to BA. So after taking AB is equal to BA, I have multiplied with A inverse on both sides. So as this is associative law, as G is a group, associative law holds, and this is E, and after writing this one I have multiplied A inverse. See here, this is A inverse, from the right hand side I have multiplied, and after applying associative law, and this is E, and we got A inverse and B commute each other. So they are satisfying the commutative law. And the next thing here is we have to show A and B inverse commute. So from proof 2, I have taken A inverse. So we have taken A inverse and B commute, and therefore we got this one, that is A into B inverse. So A B inverse is equal to A inverse B, and after applying inverse on both sides, so we got A B inverse is equal to B inverse A, which is equal to A into B inverse commute. And next one, according to the proof 3, we got as A comma B belongs to G and G is a group, AB commute. So AB is equal to BA. After taking whole inverse on both sides, B inverse into A inverse is equal to A inverse into B inverse, and we say that A inverse and B commute. So this is about the first thing here. And the next thing here is, now we have to show that in a group G, if A and B belongs to G, if you take AB whole inverse is equal to A inverse into B inverse, if and only if G is abelian. So this is if and only if case. So we have to take this one for first time and we have to prove that G is abelian. And again we have to take G is abelian and we have to prove that AB whole square is equal to A square B square. So there are two parts here. In a group G, if A and B belongs to G, AB whole square is equal to A square B square, then G is abelian. So we have to show that G isn't. Now I am going to consider this one. So suppose, see here, suppose AB whole square is equal to A square into B square. And now to prove that, so what we have to prove that? To prove that G is abelian. So G is already a group. It satisfies closure, associativity, identity and inverse. For proving it is an abelian, we have to show it satisfies the commutative law. So here, what is given here? AB whole square is given as A square into B square. And now this can be written as, AB whole square can be written as AB for 2 times, and here A for 2 times. A square is nothing but A for 2 times and B for 2 times. And now this time I am interchanging, that is A into, I am writing these two BA for at a time, and here this one also A into AB into B. And now see here, if I make a left cancellation, if I use the LCL, left cancellation, so what is left over? That is BA into B, which is equal to AB into B. So if I apply right cancellation law, so this is the right cancellation law. If I apply the right cancellation law, what remains here? BA is equal to, see here, BA is equal to AB, and therefore we got AB is equal to BA, AB is equal to BA for every A comma B belongs to G, and therefore G is commutative. So we say that commutative, and we say that G is abelian, and hence G is abelian. Clear? So I have taken AB whole square is equal to, see here, I have taken AB whole square is equal to A square B square, and I have shown it satisfies the commutative law, and therefore G is abelian. Now here we have to suppose that, conversely we have to suppose that G is abelian. See here, conversely suppose that, there are two parts here, conversely suppose that G is abelian this time. I am taking G as an abelian, and to prove that AB whole square is equal to, this is A square into B square. And now consider AB whole square. So this time I am taking this one, AB whole square I am considering, and this can be written as AB into, this one is AB, and this can be written as AB into BA into B, since AB is equal to BA. Since G is commutative, AB can be written as, so BA can be written as AB. And now this time, since it is AB is equal to BA, I am writing this as A into AB into B, and this is nothing but A into A into B into B. So this is nothing but A square into B square. So I have taken AB whole square, and I have shown that AB is equal to B square, and therefore now AB whole square is equal to A square into B square. And see here, I have taken G as abelian, and I have proved AB is equal to B square. And therefore, according to our theorem, so AB whole square is equal to A square into B square if and only if G is abelian. So if and only if case has two parts. The first thing here is we have to suppose AB whole square is equal to A square into B square, and we have to show that it satisfies the commutative law, as G is already a group, and therefore this is G is abelian. Now conversely suppose that G is abelian, and we have to prove that AB whole square is equal to A square into B square. So I have considered AB whole square, and BA can be transformed into AB, and this can be written as A into B into B. This is A square into B square. Therefore AB whole square into A is equal to A square into B square if and only if G is abelian. See here, the second one is also finished, and the next one here is we have to prove that in group G, if A belongs to G, we have to prove that order of A is equal to order of A inverse. And see, in this case, in a group G, A belongs to G. I am considering order of A is equal to P, and order of A inverse is equal to Q. Now to prove that, so what is it we have to prove? Order of A is equal to order of A inverse, which means that we have to show that P is equal to Q. In order to show it's P is equal to Q, so it is enough if we show that P is less than or equal to Q. And next one, P is greater than or equal to Q. So if P is less than or equal to Q and P is greater than or equal to Q, we say that P is equal to Q. And let's get started with our data here. So it is given that order of A is equal to, see here, order of A is given as P. And according to the definition of order, A power P is equal to E. Now I am applying inverse on both sides. A power P whole inverse is equal to E inverse. So I am writing this as A inverse power P is equal to E inverse is again E here, and therefore what is this one? This is according to the definition of A power N is equal to V, which is equal to order of A inverse less than or equal to P. So order of A inverse is nothing but, see here, the order of A inverse is nothing but Q here. Therefore Q is less than or equal to P. So this is the first case here. And the next one here is, see here, now this time I am considering order of A inverse order of A inverse is equal to Q. According to our definition here, this can be written as A inverse whole power Q is equal to, this is E, and this can be written as, if I multiply, this will be A power minus Q is equal to E. So if I apply inverse on both sides, this is equal to A power Q is equal to E here, E now. So this can be written as order of A less than or equal to Q according to our definition. What is order of A? Order of A is equal to P. So this is nothing but P less than or equal to Q. This is less than or equal to P less than or equal to Q. So this is number 1 and this is number 2, and therefore from 1 and 2 equalities, that is P less than or equal to Q and Q less than or equal to P, we say that P is equal to Q. What is P here? P is nothing but order of A. See here, P is nothing but order of A and Q is nothing but order of A inverse. And this is how we have to prove and show. See here, this is also very easy. In a group G, if A belongs to G, then order of A is equal to order of A inverse. So let us consider that order of A is equal to P and order of A inverse is equal to Q. And see here, we have to show that P is equal to Q. So here, it is enough if you show that P is less than or equal to Q, and next one is P is greater than or equal to Q. Then we say that P is equal to Q. So from our equation, that is order of A is equal to P, if I take, this can be written as A power P is equal to E. If I apply inverse on both sides, then this is A inverse whole power P is equal to E. Then we say that order of A inverse less than or equal to P, Q less than or equal to P. And if I take order of A inverse is equal to Q, so this can be written as A inverse power Q is equal to E. That is A power minus Q is equal to E. If I apply inverse on both sides, that is A power Q is equal to E, and this is nothing but order of A less than or equal to Q. So P less than or equal to Q. From 1 and 2, see here, P is less than or equal to Q and Q is less than or equal to P, and therefore P is equal to Q. What is P here? Order of A. This is order of A inverse. So this is also very, very important. And the next thing here is the order of any integral power of an element A in a group G cannot exceed the order of A. See here, this is also so simple that the order of any integral power of an element A in a group G cannot exceed the order of A. That is order of A power less than or equal to order of A. See here, G is a group and order of A is given as n. So m is an integral positive integer, that is A power n belongs to G. Now we have order of A is equal to n here. So this can be written as A power n is equal to E. So according to our definition, A power n is equal to E. Now I am multiplying both sides with an integral, a positive integer m. So this is A power n. So this can be written as nm is equal to, this is E power m. So this can be written as m into n is equal to E. So this can be written as A power m whole power n is equal to E. So which can be written as order of A power m less than or equal to n. So this is order of A power m less than or equal to, this is order of A, and therefore we say that, the order of, the order of any integer, any integral power of an element in A in a group G, cannot exceed the order of A. So this is proved here. So it is so simple that the order of an integral power of an element A in a group G cannot exceed the order of A. Let G be a group, order of A is equal to n. Let m is a positive integer, A power m belongs to G. So I have taken A power n, order of a is equal to n. According to our definition, a power n is equal to e. So this can be written, so this can be multiplied both sides with the power m, that is a power. So this can be multiplied, this is a power n whole power m is equal to, this is e power m. So this can be multiplied, that is n into m. So this is e power m. So this can be written as m into n. So this is a power m whole power m. So this can be written as order of a power m less than or equal to n here. So this is nothing but order of, see here, O means order of any integral power of an element in a group G cannot exceed the order of an element A. So this is how we have to prove these four are the most important theorems or problems which are repeatedly asked. And if you really understand, please practice. Definitely you can solve by your own, and definitely you can score more and pass it on to you as many friends as you can. So that is the greatest help needed to this channel. And please go to the playlist. So many videos are uploaded for your preparation. It will be damn easy if you follow those. Thank you so much for watching and staying till the end.